Hello, everybody. Welcome back to Computer Organization and Programming second week and second class. And I hope you guys enjoy the course so far. It's been 3 classes, and you already have one lab. You had already a one lab, and I hope you have no difficulty doing this lab, doing that lab, and you're gonna have another lab this week. So today we're going to continue covering chapter 2, and hopefully that's going to help you with your lab 2. And you will notice that the labs actually are ahead of lectures, and that is made by design. So that way you guys going to be prepared when you come and watch the lecture or read the chapters. You already have some knowledge. So hopefully the lecture, the reading, and the labs and their assignments, they're going to help you put all the knowledge together. Okay. So what we did in the last class, we mainly focus on the addressable memory because we were looking into the execution environment of the X86 architecture. And today we're going to focus mainly on the general purpose registers. So this is what we did in the last class. If you remember, we talked about addressable memory. So if you give us a 4-address bus, we can address a memory of size 16 words, and that's basically 2 to the power 4. That's what we explained in the last time. If you give us a 32-bit 2 to the power 32, then we're going to do 4 billion words. So that's going to be a large area, and this is going to be not only 4 lines, but they're going to be 3, 4, 5, and so on and so forth. So there's going to be wires in there. Going to be 32 wires, and each wire represents a bit. Okay, and if you give us just 20, so 2 to the power 20, right? So you're going to give you like 1 million. This is 4 billion. Okay, 4 billion words instead of 16. Okay, but the idea is to reducing the scale, so that way you're gonna feel what is it like. Okay. All right. So we're gonna continue in the environment, the execution environment. So now we know the memory. We know that the address is a key thing. The more address bus space you provide as an architecture, okay, the more space that you can address. And then the larger the program that you're gonna hold in this memory. All right, so now that is the main memory. Now we wanna look at the registers, right? This is something new, maybe you haven't seen before, okay? So a register is a space inside the microprocessor, and this space is divided based on names, and those names represent a space, and this space represents different sizes. So this is what we're gonna cover today, okay? Part of what we're gonna cover today. All right, so we have EAX, EBX, ECX, and EDX. This is like general purpose register, and we have base pointer, stack pointer, and we have source index, and we have destination index. These are also general purpose registers as well. These are the ones that we use to move data, do simple operations and everything. This register, stack pointer, is special, base pointer. We use them for specific purposes. These ones, you can use them as EAX, EDX, ECX, and so on and so forth. Okay, we've been talking about the flags. Remember when we talked about if you give you an 8-bit, right? So that's 2 to the power 8. Okay, let's say this is AL register, and then you're gonna have 256, right? Things that you can represent. So if you want to represent integers, 0 to 2 to 5 to 255. So this is going to be 256 combination or patterns or combination of things, okay? So let's say if we say 255 plus 1, we talked about that last time, so it's going to be 256, right? This is out of range. So this E flag, it has 32 bits, and every bit represents something, okay? Some operation. So this is maybe overflow flag, okay? Or this is maybe carry flag. Since this is unsigned integer, this bit is going to be 1, is going to be set to 1 because we exceeded the range. So we're going to talk about the E flag in more details. And this is the instruction pointer. These are the heart of the microprocessor. okay, in terms of making sense or in terms of making decisions. These are mainly for the storage. Okay, this is going to be very important later when you're going to talk about procedures, base pointer and stack pointers. Okay, but these two, along with those, are mainly made for storing. Okay, so the instruction pointer is responsible for pointing at the .code area. I'll talk about that in a second, and then we're going to talk about it from now to the end of the semester. Those registers are made for pointing at the segments of your program, like the code segment, stack segment, data segments, extra segments, okay? So we are not gonna use them in this class, but it's good to know what they are, okay? So they're 60-bit segment registers. If you wanna know exactly where your code is in the memory, the address is always stored right here, okay? But there are better way to identify the code segment, okay, using different techniques. So these registers have been part of the X86 for quite some time, and I did not see any removal, and that's due to the legacy code. Some legacy code, they still use them, but we are not gonna focus on them at all, okay? So when I talked about a register, when we talk about a register, we're talking about space, okay, where you can store data. Just keep that in mind, this is a memory. And you can access this space as a 32-bit. If you want to do this, you're just going to say move to EAX 20,000. So that's enough space because this can take up to 4 million. Oh, sorry, 4 billion. So this is okay. Even if you're going to say 50 million, that's fine. You still have a space. If you say this is too much and performance is something important for you because you're going to activate 32 wires to get data inside here and out of it, you say this is too much. I don't need this space. I only need 16-bit. That's enough. Okay. Then you're just gonna say move to AX 20,000, right? So you have now to think about one thing. So what is 2 to the power 32 in terms of unsigned? Sorry, to the power 16. Okay, so that's going to give you like around 32 something thousand. So that's still within the range. Okay, but if you want to store sign here, this number is going to be divided into two parts, right? It's going to be divided into two parts. Okay, one part is going to be for the positive range, and one part is going to be for the negative range. Okay, so just keep that in mind. If you say no, I want to even get small space, move to AL 20,000. That's not possible because AL, the maximum can take 2 to the power 8, which is 255 if it's signed, and 127 if it's signed number. If it's unsigned, it's going to take 255. So this is too much. If you want to store this number, then you have to use AX. So the bottom line is you can use this space as 32, you can use it as 16, you can use it as 8. For what? Not all registers, AX, EBX, ECX, and EDX. And you should know the naming, okay? So you should know them like your name. If you want to access 16, it's going to be instead of E means extended. So it was 16 and they extended it to 32. And this is going to be 8 bits. So this AX is going to be divided in two parts. This is AL, just as a register. Now it's 2 registers. So if you look at the whole space, 1, 2, 3, 4, so it's as if you have 4 registers, where you, in fact, just point at this space by one name, which is EAX. Okay? Is that kind of clear, guys? All right. So this is AL. And this is AH. This is the high and the low. H stands for the high, L stands for the low. And the same applies for BX or CX or DX register. Okay. So the space right here. Okay. Okay. If you look at the this diagram right here, that explains part of what I was talking about right now. Okay, so this is like the whole space EAX, and this is going to be the AX, and this is the AH, and this is the AL. Okay, so this is a number that's stored. If this number the whole number, you want to store this large number, maybe similar to this, then you need maybe the EAX. If it's a half of it, maybe it's AX. If half of those, then maybe it's AL and AH. Okay. So the other registers, the index and the base registers right here, you can access them either in 32-bit or 16, so they don't have 8-bit. That is a decision made by X86. This is how the architecture works. Okay, so if I say SI, move something to SI, or DI, try not to say, no, I don't know this register. This is a register. So ESI or EDI 32-bit, SI and DI is going to be your 16-bit. Okay, so if you see the name, you should not be surprised. All right, so this is what it is. The same applies for the stack pointer and the base pointer. These are very special registers. We're just going to use them when we deal with the procedures or with the methods. Okay, so they go with the 16 bits or 32 bits. Okay, and I forgot to mention something very important, that the numbering of those registers goes from right to left. And you notice that this is low, this is high. So it's going to go from 0 to 31. Okay, so if you have your register right here and it's AL, it's going to be 0 to 7. This is bit 0, bit 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 bits. You store a number like 0, 0, 1, 1, 0, 0, 0, 0. This is 14, right, guys? 1, 2, 4, 8. Sorry, this is 12. Okay, so you're storing 12 right here. So this is how you store it, right to left. So just keep that in mind, okay? All right. So this is what we talked about right now. So this is just the accumulator. EAX, they call the accumulator. If you want to use it the best, because they made it with a specific purpose, it's mainly for arithmetic operation, multiplication, divisions, arithmetic like addition, subtraction. Then always try to use EAX. There is no harm to use ECX or EDX. But if you want to make the best out of it, because nowadays the architecture made it very clear that all registers can be used in any way you want them to. So this ECX, we're going to use it when we learn the loops. Okay, so this is going to be used for the counters. ESI and EDI, we're going to use them by high-speed memory transferring instructions. So when we're going to move data indirectly, we're going to use those ESI and EDI. They are going to be very handy when we move into more advanced topics in the upcoming weeks. Stack pointer, we're going to talk about the stack pointer in more details, and the base pointer. These are related. So these are mainly for the methods, local variables. So you know, guys, that by now your program is going to be code, right? When you have your code, and part of the memory is going to be your data, correct? And then also you're going to have your stack. You might wonder why we need space for a stack. Because if you have a method one, right, guys, and it has integer A and integer B right here, right? And if you have here, let's say integer C equal to 5, and you have whatever, let's say C equal to A plus B, let's say it's question mark in here, it's 0. Okay, so what is C? Okay, so C is the local variable. So if it's a local variable, the data only store global variable. Okay, but this is a local variable, and since it's a data, we have to store it in a local space, right? So where is the local space? So if you go to the main function, if you have noticed that, right, guys, when you do your basic programming, if you have a data inside here and you say integer A, okay, and you have integer B here, what is the difference between this B and this A? So you know this is global and you know this is local, right, guys? So when it's local, it's going to be declared inside the stack. This is how a computer program works. Okay, if it's B, that's a global data, then it's going to be stored in the data. If it's a code, then it's going to be stored in this part. You see what I'm talking about? So this is something that you need to keep in mind. Okay, we have something else that's hidden. We call it .base. Okay, so you're going to talk about that in more details. Okay, because if you have a global data initialize or uninitialize, it is going to vary based on the architecture you're dealing with. Okay, so that's exactly what the stack is. So if we want to refer to the stack, data inside the stack, like here, how can we access the stack? How can we access the data? That's easy. We're going to say A, right? And then we access it, because A is going to be declared here, since A is or B are going to be maybe a public data. Okay, but if we want to access the stack or where the stack is, we need a pointer. So that's why we have a stack pointer and a base pointer. So these are they're going to lead you to the stack, and they're going to allow you to manage the stack in more details. These are the function parameters and the local variables. These are the two things. Okay, so both of those registers, they help us manage function parameters and local variables. These are the parameters like integer A and integer B. If you want to pass them, you need a stack. If you want to declare local variables, you need a stack. If you want to manage the stack, access the stack, then you need the stack pointer and you need the base pointer. Okay, we're going to talk about this in more details. All right, if you see this diagram right here, maybe a little bit scary, I mean, in terms of details, but you will see like at the end of the semester, you're going to feel like this is pretty straightforward, hopefully. But I promise you from now, stack is never easy. Okay, it's always complex in the beginning. And then once you invest some time and keep pushing yourself a little bit, it's going to be very interesting. So if you look at the diagram right here, you'll see these are the parameters. This is we call return address. If the main calls another function, let's say M1, 5, and 6. So this is what we call 5 and 6 are going to be pushed here, parameters. And if we want to return to the main, because we want to go to M1, and later if we want to return to the main, we want to know where we were at the main function. We're going to use the stack to store the return address. And we have base pointers. We can use them in multiple ways to point at different frames. We will know what stack frame is. And these are maybe going to be a local variable area. So you see the stack pointer and the base pointer, they're going to help you handle the stack area. Okay, so just keep that in mind. These are the segment registers. I talked about them already. Just look at them and read them in general if you would like to, but we are not going to focus on them at all. Okay, and now we're going to go to the key components of any microprocessor, the instruction pointer. Okay, so in Linux, they call it program counter. Okay, here we call it instruction pointer. Keep that in mind. You're maybe watching a video or something or reading a book about assembly language or architecture, they might not call it instruction pointer, they might call it program counter. So they mean the same thing. So if you have a code inside the memory, right, like this, and you want to know where you're at right now, the instruction pointer is going to tell you are right here. These are the code, right? These are the instructions in this code, right? So it's going to tell you are right here. If you go and you call this function, automatically it's going to go and point at the next instruction. So the instruction pointer is always going to point at the dot code area. So now that is the instruction pointer. Now you know exactly what the memory is, right? If you have the stack, this is the stack pointer. Is always going to point at this dot stack area. Okay, and if you have dot data, you can access them using the variable name right away. Okay, so the instruction pointer is very important. You need to know this registers very well. And every time you fetch, decode, okay, once you fetch and decode, these two cycles, they're going to affect the instruction pointer. Because when you say execute, the instruction pointer is going to go to the next instruction because you executed this. What's next? What's next is going to be another fetch, decode, and we're going to see if we need to fetch another memory from the data. And then we're going to do what? Execute. Once you hit execute, the instruction pointer is going to go to the next, waiting for the next cycle to execute the next instruction. So it always points at the next instruction. Keep that in mind, okay? All right, so now if you look at the big picture, if this is your program, remember the whole memory right here, it's just one memory. We divide them into parts just to show you that, okay, how those registers work together. So if you have a function that's your code, you can access the code using the instruction pointer. And you will see that today, I mean, on Friday, when you're gonna do lab 2, you will see how the general purpose registers are laid out and what values are stored in, and keep your eye on the instruction pointer as well. Okay, so this is gonna take you to the to the dot code. This is the base pointer and the stack pointer. They're gonna handle the stack. The heap, if you wonder how can we access the heap or what the heap is, every time in Java, you say new object1 and you provide whatever, I'm sorry, say object1 new, and then you say object, okay? Every time you do this, this object is gonna be created in the heap memory. And if you wanna access this heap memory, you're just gonna say object1, I'm sorry, this is one, dot whatever the method is. So this way you are accessing the heap when you say object1. And if you have a global variable and you're gonna say A is byte and you're storing 5 in A, that A is gonna be a general public data, then it's gonna be stored on data. So you're gonna access it using the variable because you declared this under the dot data. If you declare this under the heap, like you're gonna say object1 equal to new, and you have object, whatever the object that you wanna create, because since under the heap, it will go to the space right away, okay? So this is what the big picture is for the architecture, the X86 architecture. So now we know the general purpose register, we know the stack pointer plus the base pointer, right? And we know the instruction pointer. These are very important, right? These are straightforward: EAX, BX, ECX, EDX, and ESI, and EDI, right? These are the general purpose. And then we also have stack pointer ESP and instruction pointer EIP. All right, now we're gonna look at the E flag. This is a register, you see it? It's a 32-bit, start from 0 to 31. If you count this 32-bit register. These are the flags, right? If you remember, this is the overflow flag we talked about. This is the 0 flag. If the result is 0, this flag is gonna be set. Okay, so each flag is a single binary bit. So the E flag register has multiple bits, 32 bits, and every bit represents something. We call it a status. If you are looking for overflow, if you are looking for result to be 0, if you are looking for whatever the thing is, if you want to know the status of the operation, you have to go and look at the E flag. Okay, and you will see like this E flag is used to make most of the decisions. And the loop instructions, if statements, everything is made based on the E flag. All right, so when the value is 1, that's what we call the E flag is set. And when the value is 0, that's when we call the E flag is clear. Okay, so this is what we call the arithmetic, the carry flag and the 0 flag, the sign flag, whether the result is positive or negative, and so on and so forth. These are made for the system flags, okay? We're gonna talk about this in more details, okay? And these are reserved flags. So if you are writing, if you are doing advanced programming, you can use those flags for your own purpose, okay? Things that are not captured by those, neither system flags nor in the arithmetic flags. So you can do them in that way, okay? You can use those in the way you want, okay? You don't have to have those, only those flags, okay? So if you look at this table, it explains every flag from 0 to 31, and it's a carry flag, reserved flag, parity flag, and then auxiliary flag, and 0 flag, sign flag, trap flag, and so on and so forth. You'll see this is a status. That means this is arithmetic mainly about the operation. You're adding, you're subtracting, okay? You're multiplying, you're dividing. And if you look at this, this is control. And if you look at this, this is system. So this is related to the operating system. Okay, these are mainly for the arithmetic, to the related to ALU, okay? Okay, so these are what we call the status flag, and we're gonna focus on them in more details from now onward, arithmetic and logical flags. So they're gonna be the carry, the overflow, you're gonna do those, or you're gonna look at them in Microsoft Visual Studio. We're going to also look at the sign flag, and we're going to also look at the 0. So these are like the basic arithmetic um, flags, which we call them status flags. Okay, so when we did the two's complement and the sign and unsign, and in your first lab, you also played with those carry and overflow flags. All right, and this is like the parity flag. We're going to cover them in more details later. And this is what we call the let me see. This is what is the X86 architecture, right? So we covered the E flag, the instruction pointer, general purpose. We said we are not going to cover this, right? So now we are focusing on this part, okay? So this is mainly for the floating point, okay? So this is going to be mainly for the floating point. Those registers are for the integer, handling the integer, okay? And this is for the floating point. So when you say integer A, you are actually only using this part. When you're going to say float B, you're only using this part, okay? So you're not going to use those. So the CPU really has a specific hardware to handle integers in terms of E flags and everything. Here they have their own E flags. You can see it in there. Okay, I'm going to talk about this in more details, but from now to like at least 2 to 3 weeks, we're going to focus on the integer part and on this part right there. Those registers, we are not going to focus on them. This is when you use multimedia. Okay, and you need to store video and audio, and in case in the future, if you do embedded systems, you might need to deal with those, but this is what you're going to focus on: integer, general purpose, and specific purpose registers, and we're going to focus on the floating point. And when we say the floating point right here, registers, it is a space right here, and this space of size what? 80-bit. And we're going to access them using this name, ST0 to ST7. So we have 8 registers. And this is mainly made for the floating point arithmetic. All right, we're going to cover those, as I said, in more details later. All right, so with that, now we know the basic memory architecture in terms of addressability. Remember those 4 bits. And then now we know the general purpose register, the specific purpose register. So now you know what the CPU is, what's inside the CPU, okay? So we're gonna move a little bit now into the memory management. So if we talk about the memory management, we already talked about the modes, right? So we mainly focus on the protected mode. And when we say about the protected mode, we're talking about the space of the memory that's managed by the operating system. So this blue area right here, it is a space in the memory that is not managed by the operating system. So who is going to use it? Well, every time you say new, so majority of the heap memory, it's going to be in this spot. So the heap is going to be created in this. Why? Because this is an open space. The operating system is not going to manage it. So if you're going to use heap, so you have to use new, and new function is going to manage actually the heap area. Okay. So as I said, when you take the operating system class, you will understand more about the memory management. Okay. And keep in mind, though we're going to focus on the 32-bit, we're going to touch base a little bit with the 64-bit. So there is also a possibility that not only having 32-bit to address a memory or the size of the registers, but also the 64-bit is possible. And this is commonly used nowadays. 32-bit is kind of old a little bit, but teaching 64-bit microprocessor is a little bit challenging. Okay. So 64-bit is the same as 32-bit. It has like compatible mode, and it has 64-bit mode as well. Okay, so the registers, instead of EAX, now we have racks. Okay, so instead of saying EAX, which is 32-bit, now you're saying racks. The name is different, 64-bit. Okay, and instead of saying EIP, the instruction pointer, extended instruction pointer, you have PRIP. Okay, so this is like 64-bit instruction pointer. All right, guys. So when you are working with the 64-bit general purpose register, you're going to include the 32-bit. In addition to those, you're going to have R8D, R9D, up to the R15D. So these are all general purpose registers. Okay. If you're talking about 64-bit, you're going from racks to RBX, RCX, and so on until you get to from R8 to R15. So you have more registers in terms of numbers and in terms of space. Okay. And these are like the names of those registers. You can call them R8L, R9L. So these are 8 bits, 16 bits, 32 bits, and 64 bits. These are all available registers when you are in the 64-bit registers. So you're going to have one simple program, maybe the third or the fourth week, when you're going to see what it looks like when you program in 64-bit. But for now, we're going to focus on the 32-bit. Okay. So we know that the microprocessor and we know the microcontroller, right, guys? Remember the difference between those? So we are focusing on microprocessors, right? So we know that in the microprocessors, the I/O systems and the memory are outside of the microprocessor. In the microcontroller, everything within the chip, right? But in this part, everything is out of the chip. If it's out of the chip, then it's going to be within a component, or those components, they're going to be within a system, right? So this is what you're going to focus on right here. So you're just going to focus on the motherboard that holds almost all the components that X86 microprocessor requires. Okay, the microprocessor X86. And if you want to know more details about video and memory and so on and so forth, just refer to refer to the book. And I will cover the input-output ports as well. Okay. So if you look at the motherboard right here, it has those components: the CPU, external cache memory, main memory, BIOS, basic input-output system, and it has those parts as well. So let me go to the picture and show you those parts, okay? So this is like the main motherboard. This is very old, but at least it shows you the main component, okay? And this is what really matters, the microprocessor. This is the microprocessor slot. We don't have the microprocessor. So these dots, you see them right there. They're going to have the pins that they come out of the microprocessor. It's like a square, and it has pins like this. Okay, so these pins, they're going to come in. You can just install them right here. Okay, so this is Pentium 4 socket. This is the main memory. So this is the I/O system along with the main memory. Okay, this is the PCI for the output. This is mainly for the monitors. This is mainly for the video output. This is for the audio output. You see this is the printer output, okay? And this is for the hard disk, okay? And this is for the power. This is for the I/O controllers, okay? And then you have the keyboard right here, the input. That is the keyboard and the mouse, okay? So the whole microprocessor depends on having this motherboard. Okay, so when you install it right here, it's going to control the I/O and the main memory. It's going to communicate with the main memory. It's going to communicate with the I/O. So that is the microcomputer system. Okay, unlike the microcontroller, this is like a microprocessor system. It requires to have the I/O and everything on the board. All right, is it kind of clear? So if you wonder about the battery right here, why we need a battery right there. So this battery, there is every time you switch on the computer, you have the BIOS, the basic input-output system, and you have the post. These two systems, they are part of the operating system. So they're gonna run before the operating system. So when you switch on the computer, you're gonna see a black screen and sometimes yellow or white text is gonna be printed on the screen. This is because of the BIOS and the post. So the BIOS and the post first is going to run, and then the BIOS is going to be the second. So the post is going to check the components. If there is a single electronic or electrical component damaged, this system is going to report it. And if that's the case, the system is going to shut down. You're not going to go to the next step. Okay? If the post system says all parts work fine, then you're going to go to the BIOS. So the BIOS is going to make sure that the I/O system addresses and everything is known to the microprocessor. And then the BIOS is going to now give the control to whom? To the operating system. And then the operating system is going to be loaded from the hard disk. This is a connection to the hard disk. So there's going to be a hard disk in here when you're going to have the OS. So the BIOS is going to go there, take the operating system and load it to the memory. Once the BIOS upload the operating system to the main memory right here, then it's going to say see you later. So the operating system is going to take control, and then it's going to communicate with a microprocessor, and then they're going to agree in how to operate the entire system. Okay? So if that is the case, then now your programs are going to be in the hard disk, and the operating system now is going to go to the hard disk, get things in and out of the memory and execute them and help the microprocessor execute your programs. So the operating system is a key class, guys. So you really need to take it, and you really need to master it. Okay, so now we know what we are doing before we start programming. The only thing missing is the I/O. So we know registers, we know memory, we know addresses, we know modes, and we know the system surrounding or supporting the microprocessor and everything. So now we want to look at the I/Os. So when we talk about the I/O devices, again, microprocessor and memory, this is like the main components of any architecture, right? And then we have the I/O, right? So this I/O handles the disks, the monitors, the keyboards, the scanners, and then modems, whatever. Okay, these are all I/O devices. And the I/O devices are always connected with the memory, with the control of what microprocessor. And you know, remember, we have address bus, data bus, and control bus. This is read or write, what you want to read from, and how to transfer the data, which is the data bus. Okay, where you want to read from, which is the address bus. Read or write, decided by the control bus. Okay, so keep that in mind. These are very important components, right? So we want to know what is the relationship between I/O and assembly language, right? So if you look at the big picture right here, you're going to have the system bus. This is the microprocessor right here, and the microprocessor is going to communicate with the I/O devices through the system bus. So there is no direct, actually, communication between the microprocessor and the keyboard. There is something we call what? I/O controller. Okay? So if you have ever installed a new device in your computer, they're always going to ask you for what? The device driver. Okay, so driver is the I/O controller. It's a software controller. So there's a hardware controller and there's a software controller. And this I/O controller, if the CPU needs to communicate with the I/O and the I/O is busy, then the CPU is going to be informed that using the status right here that it's busy, please try again later. Okay, unless if there is some priority, the microprocessor maybe say, hey, it's a priority, stop it and listen to me right now. And these are the commands that available to operate this device. They're going to be provided right here. And this is the data that you need to store. Either you bring to store right here, or you bring from the I/O and you want to send them to the microprocessor. Okay, so this is the whole idea of the I/O. So you need to have a controller, and this controller is going to operate the device and communicates with the microprocessor. Okay, so remember the BIOS, the basic input-output system, is also part of the operating system, and it also helps the microprocessor to handle the I/O as well. Okay. So every time you say scanf or printf or whatever in Java, you are actually dealing with the I/O controllers. Okay, so with that, now we're going to look at a little bit more details right here. So for this part right now, we're going to look at the things that I explained in detail. So you're going to just look at what's the interface and how the I/O controller receives input and everything, and so on and so forth. So I already explained the slides, just look at those details right here. Okay, so again, you're going to be mainly either read input from the keyboard, right, or write output to the screen. That is mainly what you're going to do in terms of the I/O devices, right? So let's look at the I/O devices from the perspective of the programming language. So we have a high-level language functions, operating system, and BIOS. Okay, so we're just going to see how the I/O works with those. Okay, so if you ever thought about, let's say, when you say system, right, guys? Okay, and then you're going to say I/O, right? And then maybe you're going to say print F, right? Whatever that thing is. So when you do this from a high-level language, you're actually sending a request to the I/O, and the I/O is controlled by the operating system. And in fact, the operating system doesn't really know the details. It's going to send it to the system, which is the BIOS right here. So you're going to see at the relationship when you're actually communicating with the I/O to the hardware. Okay, so if you're communicating from the language level to the hardware, how that is going to happen. All right, so it's going to be the operating system and the BIOS, and they're gonna take care of that. So this is, if you are using a Java, that's what I explained about right now. If you say print, okay, if you say print F, or you're gonna say scan maybe F if you are in Java, and C, okay? And if you do that, then that is just calling a function, and this function is part of a library, right? So you have to say in Java import, right? IO, right, guys? You have to do this in Java, correct? If you are importing, you are in fact communicating with an operating system, because this library is part of the operating system, okay? So if you do that in the high-level language, then the library is part of the operating system. And the operating system is going to say, hey, what's printf? I already provide you with this interface, or sometimes we call it the API. And then it's going to take the details. Let's say you want to print something in here. It's going to translate it to a point, and then it's going to give the control to the BIOS. Okay, so the BIOS is going to take whatever you want to print, and then it's going to communicate right away with the IO controller. All right, so this is very important. So I will show you an example right here. So this is an application program. What's going to happen right here? This is maybe a library function. Okay, so you're calling an operating system function. So when you say print, scanf, anything that you use, or scanner in Java, anything that you use to read or write to an I or an O device, you are calling that using a library. So that's why all languages, they have import or import-like utility. So it helps you communicate with the operating system. And once you do that, then when you call the library, the operating system is going to take the printf, and then it's going to call the BIOS subroutine. Okay, and then the BIOS subroutine is going to pass, let's say if you are printing something like, say, hi. This hi is a human-like language, and the computer only knows zeros and ones. So we know H and I is an ASCII because it's quotation. So it's going to be translated into an ASCII. And we're going to decide the color, we're going to decide the size, and we're going to decide the location. This is your screen. We're going to say, is the prompt going to be here or is going to be there? If English is the language, is going to be here. If other languages, maybe they go right to left, the prompt is going to be there. And is the background black or white? And if it is the font white or black? And if it is, what is the type of the font? What is the size of the font? So this is all going to be handled by the BIOS right here. And the BIOS is going to call some subroutines to move the cursor to the next position, okay? And then the control now is going to go to whom? To the BIOS. So now the BIOS says, okay, I received the character maps, and then maps it to a particular system font, and then decide the color and everything, and then send those characters to the hardware port. And now the hardware is going to print out. It's going to be the monitor itself here. It's going to be pure hardware, right? Dumb hardware. Is going to take the data from the BIOS and is going to give it to the video controller. That's the IO controller. And the video controller is going to generate the signals, and then it's going to display hi right here. Okay, so this is the relationship between a high-level language when you write a code, and then how that's going to be translated to the hardware. Okay, so this is all part of the architecture. Okay, so if you look at the assembly language right here, if you are programming or writing a program using assembly language, you can call a library like Java, or you said, I don't care about the library. I need to communicate right away with the operating system. You can do that. You said, I don't need either of those. I just want to talk to the BIOS. You can do that from assembly language. And you can say, I don't care about the BIOS. I want to communicate right away with the hardware. You can do that as well. Okay, so that comes at a cost. So the cost right here is going to be control versus what? Portability. So if you said, I don't need these two layers right here, you write a code right away to communicate with the BIOS or to communicate with the hardware. You have more control, but your code is not going to be portable if you want to run it somewhere else. Okay, so it's like that's the whole idea of you saying import in Java. When you say import, it doesn't matter what the IO controller is in there. It doesn't matter what the size, what number of bits, is it, how the IO controller works, is it an updated software? You don't need to worry about that. The operating system is going to take care of it. In addition to the BIOS. Okay, so if you do that, that's going to be something portable. So you can write code anywhere you want. But if you want to create your own library, you can. You have more control. But if you want to make it portable, then you have to add it as part of the operating system. Okay, and this part explains what I already talked about right now. So you can do that by calling a library, importing, or by calling an operating system, or by calling the BIOS right away, or by sending things to the hardware without any of these components. Okay, so with that, I hope by now you understand the big picture of the computer architecture. So we know what is a microprocessor, and we understand ALU, control unit, clock, registers, and we understand the memory, and we understand the cycle, the execution cycle. And when we talked about the execution cycle, we'll also cover the main memory read and write cycles in there. And we also talked about the general purpose registers, and we talked like the microprocessor needs to have a system that's going to provide it with the I/O needs. And we also talked about the I/O. So I hope now you are ready to hit the ground running in terms of writing a program or programs. And this is something that you're going to do this week. You're going to learn how to create programs, and you're going to see those registers. You're going to deal with the I/Os, and you're going to see almost everything. Okay, we talked about in this chapter. All right. So this is it for today. So I will upload those video in iCollege, and I'm gonna meet with you at 1:15, just in case if you have any questions. All right. So thank you for now, and see you later. Thank you, guys.